Hello, everyone. Welcome to the class. So you guys are section 2 going on. All right, so today during the first half, we're gonna do a lecture, and then during the second half, you're gonna do your presentations for your GPT. Okay. Um, so that's kind of the plan. The topic for today with you guys, I think I've done regression already with the wine quality data set, correct? So we've done that one. So we're almost done with that sequence. We just have to do one last idea, which is we're going to take the same wine quality data set that we use for regression, but now we're going to switch it to classification. All right, so I'm using the exact same data set, and the idea being that you'll see the contrast, right? So you'll see the contrast between regression and classification, even though we're using the same data set. So definitely an important thing. As I've said several times, these scripts, the classification with iris and regression with wine quality and classification with wine quality are three of the most important in the whole class, right? You really need to master these because there are a lot of the fundamentals, at least as far as applying this to solve problems. All right, so we're going to get started. So, and like I said, I'll finish, I'll do this first half of the period today, and then during the second half, you guys can do your presentations of the GPT. Just bringing up my script here. Also, I remind you, so we are on week 9. So the next exam is going to be on week 12. So you still have time. There will be a third homework assignment. Look for that sometime this week. I think I've mentioned this already. It's going to be 2 problems, a regression and a classification problem, but you can choose your own data set, right? So find a data set for regression, find a data set for classification, and then you're going to implement those algorithms, and you need to deploy it. So today I'll show you a little bit about, or I think I already showed you how to deploy with Onyx. I should have done that in the regression one. Yeah, so right. I did that last week. I'm just getting confused because now both sections are kind of off. But yeah, I did that with them on Monday, and I did that with you guys last Thursday. So you deploy the model, and then I still need to show you how to take that deployed model and then build a website. So I'll do that next time. But yeah, the homework assignment is essentially a regression problem and a classification problem. You get the data sets, you need to do the models and everything, evaluate performance, and then deploy both models to the web, to something like GitHub pages. Are there any questions about that? All right, great. All right, so we're going to need to use Colab. So let's go ahead and start Colab. Notebook. Okay. Yeah, go ahead. Yeah, so I went over a little code snippet that allowed us to take the model and export it into a .onyx file. So that I've done here. I just haven't shown you how to take that and then use it in a website. So I'll do that in the next class. Okay. But I want to finish these scripts today. So next time we meet, we'll have more time. So I'll do logistic regression and this, and I'll show you how to do that on the website. All right, so I'm gonna mount the drive. This should be pretty easy because, like I said, in the beginning, it's a lot of new information, but now it starts to get very repetitive, right? So you'll see how we've already done the script for wine quality data set when we're trying to model a regression model. Now I'm just switching it to classification. So 80% of the code or more is the same. Okay, so here is the drive. I'm going to copy the file. Same one, wine quality. Copy path. Okay, I'm going to paste it in here somewhere. Okay. And now we should be ready. This is a good opportunity again to remind you that we are in this module here, and you should be reading all these materials, okay? So I gave you a lot of material here for you to read, chapters 2, 3, and 4, right? You're responsible for that. It goes in, this is like the essence of machine learning, right? So make sure you're reading these. I also provided a PDF version of it. It's kind of the same. And then, of course, this is the code that we're going through right now. These are the two data sets, iris and wine quality. We've done regression with NNs and XGBoost. We covered that in the last class. We exported that model with Onyx. We've covered iris classification. All we have left from this folder is wine quality classification and then cross entropy, which we will cover next week. This is a very, very important topic. All right, so we're going to look at this one. And this, as I said, just to finish out this sequence, which is very basic. Okay, so I'm going to bring in the libraries. Okay, so the same ones as before, NumPy, Torch, Pandas, sklearn, TorchNN, Torch Optim. Okay. Then we have the plotting libraries and Torch utils, train test split, same things. Okay, good. Then we have our metrics. So if you remember, when we did wine quality regression, we used what metric? R squared, right? So we used R squared. For classification problems, we use precision, recall, F measure, and the confusion matrix. This is also a lecture that I need to do in the next 2 weeks. XGBoost, we don't need XGBoost for this one because I'm not going to be doing regression, and I'm just going to stick to classification. These 3 libraries I need to install, very likely. So pip install Onyx runtime. It's tools. Okay. And SKL2 Onyx. Oops. Okay, so that should be done. So we should be good to go now. I'm going to hit run. Import these 3 libraries. Okay, good. So as you can see, the very basic idea as before, right? The parameters, whether it's regression or classification, as you can see, is pretty consistent. Batches, I'm using batches of 32 here. Learning rate, notice is 0.001. You can play with that learning rate, 0.001, 0.003, something like that. Number of epochs, that can change depending on the data. This is 1,000, and the epsilon for the scaling as usual. Okay, and I am recording the session, so you can, I'll be posting the video later. All right, so we're ready. Okay, so remember now we play with the data. As I've said several times, I intentionally picked this data set because I wanted to do both regression and classification. It's not usually a classification data set, right? It's not optimal for that. But it allows me to kind of give you the contrast between the two techniques, the differences, and in particular, things that you might have to think about. So we're going to read in the data as before. So wine quality, I need to change the path, of course. Okay, so we read in the data, and then we're going to display the pandas data frame. And here we are, right? So the problem is, what are the classes here? Do you guys see that? Do you remember that wine quality? We have the features such as acidity, sugar level, chlorides, density, pH, sulfates, alcohol. Those are still the features. There's 11 of them. And then there's one quality column, which is the target. And the rating goes from 0 to 10, so or 9. So essentially it's a 1 or 3 and so on. But we want to change this. That's a continuous range where 7 means more than 3, right? So that's important to note. But you can still model it as both regression and classification. So in this case, we just have to decide what our classes are going to be. Okay. Let me over here. So we have that. Same thing as before. I'll do the correlation matrix, just a good practice, although we've done this part before. And we can, once again, run it. And there we are. We've already talked about this. So here alcohol is the highest correlation to quality. Okay. All right. So now, same thing. We process the data. So we're going to convert it into a NumPy array from pandas. Pretty standard. You can see now you have the two pipelines for two very common problems. Regression and classification are going to be some of the most common basic machine learning problems you have, right? And this is the path that you can always follow, right? So now we can print the NumPy array. Get the data. I'll add a few more cells. Okay, we split the data now. So we're going to look at the shapes. So remember there's 4,498 samples, 12 columns. The last one is going to be used for the classes. So now we do the split. So X and Y, so exactly how we did it before, we split the data of X and Y. Okay, and we can print it. You can see Y has the quality values. This time around, if you remember in regression, we did not change the type. We use float because we were predicting real valued numbers. Here now, I can change this to integer as I'm starting to think about classes. You see that? So this is the first choice that I made with this approach. And there's my Y now. But I still don't know much about the classes. What do I know about these classes? I know theoretically I have from 0 to 10, but do I actually have that, right? You know, was 3 ever selected as a ranking? 1, maybe no, you know, maybe the one is really good, right? So 1 was never really even selected. So you have to look at that problem, okay? So what I like to, and this is where class imbalance is really important, especially in classification problems. You need to inspect that before you move forward. So here I'm going to take all the values in Y. I'm going to use NumPy unique to identify what is the set of actual values in this data. And you can see I actually don't have all the numbers. There is no 0, 1, or 2. There's only 3, 4, 5, 6, 7, 8, and 9. You want to see if there's gaps because PyTorch, the way that it works, does not like gaps in the classes. All right, so we have a gap here as we don't have 0, 1, and 2. So I need to fix that problem. Okay, so that's one of the things to consider here. Otherwise, your code will not run correctly. Will break, actually. All right, so I want to print out the length. So it's going to be 7. So there's 7 classes. Okay, that already, I'm worried because 7 classes is a lot for a classification model, right? Especially if the data is not balanced well. So we want to study the balance and think about the issues here. So as you can see, I have this, I think I had used this before. It's my same code I always use to just do a simple histogram. And if I gave you this on the exam as a question, and I asked you, what do you think about this data? What would you say? It's imbalanced. That should be the very first thing you think about. In the real world, which this wine quality data is more real world data. Yes, it wasn't designed to be a classification data set. So this is what you can expect from your data. It's not going to cooperate. It's not going to behave. It's going to look like this. As you can see, classes 3 and 9 are just almost non-existent, right? So it's a highly imbalanced data set. Look at the majority is 6. And so you have several choices here, right? If I was attacking this problem, I would just use 3 classes, probably. So I would, you know, these are so small that I would probably just use the class from 3 to 5, the class 6, and then a class from 7 to 9. Do you guys see that? Unless the people that want this analysis have other questions. So they may have more insight, right? So to them, they don't, you know, maybe they just want 2 classes. They want 7, 8, 9, or the other. Do you see that? So these are choices that you have to make when you look at data like this of how to balance the data. Now you can drop these or you can add them in, whatever you want to do. Yeah, go ahead.
What if that's left now?
Then you keep it.
Okay, so you can run.
Oh yeah, of course, it'll run, but you will see, because that's actually what I'm gonna do. I'm gonna run it like this, and the performance is not gonna be great. The model, even though it's gonna be a fancy deep learning algorithm, it just won't be able to learn these very well. You see that? Machine learning algorithms like balanced data sets. Yeah, it would be better if, yeah, exactly. Like put some salt in there and get people to rate it badly or something. You want to bring up those values somehow. So a better solution here might be to combine these 2 into this one, because 5 is probably unacceptable to the company anyway. So, and then, yeah, something like that. So balancing is important, but in this example, I wanted to show you the nightmare, right? The problems with dealing with imbalanced data sets, which is what this is for sure. So imagine another case for this would be like fraud, right? So in fraud, it'll be like no fraud, a little bit of fraud, and you're trying to build that model. So it's very complex. Do you guys see that? All right, so I have my histogram now, and I'm gonna stay with those. I'm going to stay with those. Classes. Obviously, I need to do some things to make them into classes, but I know I'm well informed now. So I'm going to proceed here. I'm going to print the shapes just so that I know what I'm looking at. Okay, so I have these. Do the train test split. I'm going to use the random seed. On my X train, Y train, X test, Y test. Okay, so I have my data there. We can print the shapes or just see them here. Remember the data type quantization issue. So I'm going to change from float 64 to float 32 for the x's, and I'm going to leave the ints as int 64. The y's, sorry, as int 64. So you can see that there. All right, so I've converted, quantized the data a little bit, and made sure these are integers. Any questions? So you can see we've done very minor things so far. Now I'm going to proceed to convert the NumPy arrays into Torch. So that's ready. Whether it's regression or classification, you always want to scale your data. Standardize it or normalize it. I usually go with standardization. And we're going to take the same approach because we're going to be deploying these models. We want to create the x means and y deviations as constants that we can plug into the class before deployment. Okay, you can see we've talked about this already, right? So we're doing means across all the columns for every column individually. So you can see here x means should have 11 values, right, for the means. So that's exactly the same. Okay, and now we can proceed. And now comes, see, a lot of this, as you can see, is data preparation and then building an architecture that is consistent with classification. Okay, so now you can see I need to address the gap issue. So I'm going to go ahead and I'll create a mapping dictionary, essentially. Okay, and we've already done this, right? We've done these dictionaries when we did stoy, atoy, right, in the LLM, right? So that simple example of the little reverse dictionaries, we're doing the exact same thing. All right, so I'm going to go ahead. I know that there's about 4,000 samples, so I can just do this. This we need to do. So why? Again, because we can't have gaps, right? So the data loader is going to be a problem with the data loader itself. That object is going to break if there are gaps in the classes. So what I'm doing here is I'm mapping, since I have 3, 4, 5, 6, 7, 8, 9, but I don't have 0, 1, 2, then I need to map 3 to 0, 4 to 1, 5 to 2, 6 to 3, 7 to 4, 8 to 5, and 9 to 6. Does this make sense, guys? Yeah. And then we do the reverse dictionary also, so that it's easy to retrieve the correct values later. All right. So that's it. So we create those. Now I'm going to need to process the data for this. And I'm going to take, in this case, the approach that I took with Iris, right, of how to create the data loaders. So you can see here, I'm creating two lists so these lists of tuples, remember that? So there's two approaches to creating the data loader. One, like we did it with the regression example, and now one going back to how we did it with Iris, right? So we create a list comprehension, which is this whole thing. And then we have a for loop for I in range of X train. So the number of samples, about 4,000. And then for every one of the samples, right, from X train using the I index, we bring in that vector of 11. And then from Y train using that index, we bring in the item. So if you remember here, we bring in 3. But that 3 needs to be converted into 0, right? So I'm going to use the label map here. Make sense? So this part here, the label map here, right? So the label map that I just created up here, just to take that 3 and convert it into 6, take that 4 and convert it into 1, and so on. No questions? All right. But otherwise, pretty much the same. So I create my 2 lists, wine train list and then wine test list. So I'm going to go ahead and hit run. Okay, and you can see now the data should be converted, so we can take a look at this. So we can grab wine train list, the first 3, and you can see we've got our a tuple of vectors of 11 for the first element, and then we have the classes 3, 2, 3. If I do maybe like 15, there's a 0. Do you guys see that? So there is a 0. So they've been mapped. Okay, great. So now, add a few more cells here. So we are ready then. We don't have to create a train DS, a data set, right? As we did last Thursday for regression. Here, because we have it already as lists of tuples, we can go straight to the data loader. You can see that there. So using torch.utils data loader, we take wine train list, batch size, which is 32 in this case, and we shuffle, right? For every epoch, we'll shuffle the data. All right, so we know the number of samples. We repeat this process for the test DL. So wine test. So we give it wine test list. Now batch size here is not going to, remember, it's not 32 because we're not training. So we can just give it all the samples all at once. There's about 1,000 test samples. That's something very easy for Torch to handle. And so notice this is different here for the training. I did batch size, which is 32. Here I do all the samples in the test set, which are basically I'm getting from here. Got it? And that's about 1,000. Don't forget this. This is a common mistake I see students do in the homework. They put like batch size here. And so what's the problem with putting batch size here? It means that when you did the test, the evaluation, you may just be evaluating over the last 32 samples instead of all the 1,000 samples. Do you guys see that? So you don't want to make that mistake. I will look for this. This is one thing I specifically look for in the homework. All right. So great. So we've prepared the data. The data is now essentially like classification data. And so that was it, right? So pretty simple. And so now we're ready to create the architecture, right? And it's going to be the same approach, but this is very important, right? That you study like the difference between building a regression model and a classification model. There's just very subtle differences. And this is where I think reading the notes that I provided is really important because I've explained that in a lot of detail for you to read with examples and things like that. So definitely read through that material. Okay, so yeah, the data is ready. Now we can start creating the neural network, right? For classification. So I'm going to go ahead and grab this one. And I have two, networks here. but I'm only going to do one first, and then I'll come back for the other one. This is where it also is useful to use the whiteboard, right? Because we want to think of how this architecture translates into the actual graph that we're doing. So remember, again, something very repetitive that we've been doing that by now should be very familiar. Every time we build a model, we want to take an object-oriented approach is the best way to do it. We create a class. In this case, MLP. Remember, we inherit the NN module. Then we have two functions, the init function, which is the constructor, and then I have my forward function. Same thing. Notice that in the init, we do the same thing. We pass x means and x deviations, which are assigned as constants, and we still do the super init to instantiate the inherited class. Now comes the architecture. Obviously, this part is going to be a little bit different between regression and classification. This has an input layer, a hidden layer, and an output layer. The input layer is the same, right? So whether it's regression or classification, we had 11 features going in. That hasn't changed. Notice that the activations can be whatever we want, like ReLU, sigmoid, tan H, GeLU. In this case, I'm using ReLU, which is what you usually use for classification problems. But you can play with sigmoid or something else. Now, in this layer, you can see that this is different, right? In regression, we had, what was the number here for the regression version of wine quality? Do you guys remember the output? What was it? It wasn't 6 for 11 is the input. But for regress, think about it. Just think about it. It's regret. This is key, right? It's regression, right? 11 features go in. What is it predicting? The quality, right?
One.
How many neurons does it need? Just one, because it predicts any number. Regression. Classification is different. We have here 7 classes. Do you see that? So we put in 7. Now, could I build a regression model that has multiple outputs? Sure. That's called so in regression, there are multi-input, single output models, which is the one we did. But you can also build a multi-input, multi-output regression model. Perfectly doable. You're the architect of it, so you can do it. You see what I'm saying? So it's definitely possible. And if we were doing that, let's say we had 3 values, then that would be a 3. Okay. In this case, it is 7. Now, one thing that is a big difference in the output layer is that regression had nothing, right? It would just predict values. Whereas classification has what? What function? The softmax, right? What does the softmax do? Remember, it makes sure that all the outputs sum to 1, right? It creates a probability distribution where all the probabilities sum to 1. So in this case, there's going to be 7 probabilities, but they should all add up to 1 essentially, right? And 1 should be the majority output. So like a 0.95 and then everything else 0.01 or something like that. That's it. Do you guys see that? So essentially, that's the difference between regression and classification as far as the architecture. And then, of course, we have a different loss function, right? Which we'll talk about in a second. Okay, so we have the forward function now. And in the forward function, we have our x that comes in. Notice this is commented out, so make sure to remove the comment because this is where we actually standardize our data, right? We've been doing this since Iris and we'll continue to do it. Notice I'm skipping dropout for now. This is something I'll cover later when we start adding all these tricks to improve things, right? But for now, we bring in x minus x means divided by x deviations, and now our data is standardized, okay? And then after that, x, which is a vector of 11, right, of batch from 1 to 32, comes in here. Then it goes into the activation function, which is a ReLU. Then from there, it goes into linear 2. So it's now 5. And now it comes out to X. And now it goes into activation 2, which is the softmax, to produce a final Y pred. So during training, the size of Y pred should be what? Who can tell me? What's the size of Y pred during training? If you take that tensor and print the shape, what would it be? Not just 7, the whole tensor, what's the shape of it if you printed it? Like if you did ypred dot shape, well, the batch size. So it would be 32 comma 7. Do you guys see that? This is very important, right? So whenever you're doing these scripts, always print those shapes. And that's the best way to truly understand everything that's going on. When we do inference, we can just give it one sample. And so if we printed that shape, it would be what? 1 comma 7. Got it? All right. So we did the MLP architecture. Done. Perfect. Okay. Now, we'll skip this one for now, and we will come back to the DLNet. Also, let me draw this architecture, actually. So it's 11, 5, and 7. So let's go to the whiteboard. So we're going to go to the whiteboard. Okay, so the architecture of this model is 1, 2, 3, dot, dot, dot. This is 11. Then we have an output here. So this is the input. This is the output. And then we have in here a hidden layer. So this one was 5, I believe. 5, right? So essentially 1, 2, 3, 4, 5 neurons. And then finally, this one has 7. 7. There's an activation function here, which is ReLU. Remember, it's called a rectified linear unit. And then here, there's also an activation function. And this one is called the softmax. So this is the softmax. Okay? And remember that what this should produce, it can produce something like 0.2, 0.4, dot, 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 0.5, 0.3. And if we look at these values, what's the problem with them? They don't add up to 1. You guys understand that? But what do we know about our real data? Our real data, if the label is 5, right? Like if that, when I created that list of tuples, right? I had these numbers 0, 1, 2, 3, 4, 5, 6. So if one of those is 5, that's what we give it in the data loader, but PyTorch converts it to the one hot encoded version of that. So I'm going to do 0, 1, 2, 3, 4, 5, 6, right? So that's 7. So if this is 5, then it's going to be 0, 0, 0, 0, 0, 1, 0. Do you guys understand? This is called one hot encoding. We don't have to do it anymore. We used to have to do this with the labels manually, but now if you notice in the data loader, when we did that list of tuples, we just provided this directly, but just know that internally, PyTorch is doing the conversion. So why is this important? Why am I bringing this up? Because if you look, if I take the sum of this, what does it equal? What is this? 1. So it represents a probability distribution that adds up to 1. But if we don't use cross entropy, the neural network can produce something like this, which does not meet the same condition of having a probability distribution that adds up to 1. So that's why we run softmax, which is just the formula, and softmax makes sure that now, it should be this one, right? So let's say that the model has trained really well. Okay, so then there's 7, right? Yeah, so 7, there's 7. Okay, so I'll just do 0, 0, and then I'll do 0.01, 0.01, 0.01, 0.01, right? So this should add up to 1. Do you guys see that? Does this make sense why we do it? So this might escape you a little bit, this little detail, right? That the reason why we do the softmax is because we want to make this one be as much as possible like this one. The real data for sure adds up to 1. So softmax makes this add up to 1. Okay? All right, great. So, and that, remember also, we did that in the GPT. So the GPT had the exact same thing over however many tokens we were using. Any questions about this, the architecture? Yeah, go ahead. Yeah, this is called one-hot encoding. Yeah. In the loss function. In the cross entropy, it's a good question. So when we create loss equal cross entropy, you will give to that function, and remind me when we're there, we will give it two things, right? We will give it ypred comma yb. Yb is going to look like that one. And ypred is going to look like this one. So that's why I was asking. So ypred is going to have a shape that is 16 comma 7. Do you see that? That's the shape of that tensor. Whereas yb is going to have 16 comma what? 1. Do you understand? 16 comma 1 because we're just giving it the integer itself.
YB, the one you're using, we're training.
That's right. During training, we give, as we are iterating, right, we grab xb comma yb from train.dl. We give xb to the model. The model predicts ypred. That's a shape that is 16 comma 7. And then yb is 16 comma 1. So those two tensors go into cross entropy. So the loss function, I usually use the term loss fn, will take in a tensor that is 16 comma 7 here, and then a tensor that is 16 comma 1 here. We can print that in a second if you'd like, but that's how it works. And it's meant to make your life easier. In the past, you were responsible for converting YB to be 16 comma 7. But now the loss function handles it for you. It's a simplification. What's that? Where do we get the YB? Sure, it's in the for loop. So where I have my 2 for loops during training. So this one was for n and n epochs, and this is for xb comma yb from train DL. We'll see that in a second. Okay. All right, great. So yeah, so that was the architecture that I just did for the MLP like this. All right, so now we can go back to the code. I'm gonna share the screen. And we'll see that. We're about to do that. Okay, so I have my architecture here, right? Now I'm gonna skip DL for now. Now I proceed to the train function, which if you notice is the exact same train function that we have been using since the GPT. It almost nothing of it changes. So you can see that train loop. It's going to take n epochs, model, loss fn, opt. You can see here are the 2 for loops, right? So for epoch in range and epochs, right? That's so that we can give it all the data, give the model all the data. And then here is for xb comma yb from train DL. Do you guys see that? So what we can do here is, so that we can visualize this, actually, I'm going to do the following. Oh, actually, I have it here. You can see I already had it in my code. So I'm just going to remove these comments. I'm going to print yb.shape, which should be what? 16 comma 1. And I'm going to print ypred.shape, which should be 16 comma 7. Do you guys agree? All right. And I'm going to put even a little input here just so I can halt the program so I can just visualize that. Everyone, any questions, guys? All right. So again, train loop has the two for loops. The first one for the number of epochs, the second one for iterating and grabbing the batches of 32 from train DL. So what do? Just like every single other example, we take XB, run it through the model. It predicts ypred. Okay. We have YB. So this part I will remove. I'm only keeping it for now for debugging purposes. And then here it is. The loss function, remember that's the place in the computational graph where I'm going to connect the predictions with the real data. So the loss FN takes in ypred, which is the predicted tensor, and YB, which is the real tensor. Calculating the difference, right? Now, what loss do we use here when we did regression with wine quality, we use mean squared error, and I went over that, how it works. Now for classification, we use cross entropy. I still need to talk about those two things, so we're going there, and I do have that cross entropy Jupyter notebook. All right, so once I calculate the loss FN, what do? The 3 lines of code that do all the heavy lifting. The reason why we have PyTorch, right? Remember, we always use these. So zero out the gradients, clear any accumulated values. Loss backwards, what do we do here in the computational graph? We use calculus to calculate the derivatives. The information that is given is whether we're going to add or subtract. And then after that, op step does what? Updates the weights with the learning rate, right? So the learning rate is how much we're adding or subtracting. And then here, we're just printing out every 20 epochs, or 50 epochs, I should say, the loss. Our goal is that loss should be going down. As you can see, this is exactly the same thing we've done before for regression classification. Doesn't really change, right? The format. Now, what's going to change is in the next line of code, when we instantiate the loss, you can see these are, I usually call this the core functions, where we bring everything together. And you can see here, I'm going to be using an MLP net. So I instantiate it with the X means and X deviations, and that's my model. Done. The optimizer is the same. I'm using Atom optimizer. Remember, I link the model to this, right? To these parameters, okay? So this represents how many weights and biases I have. And then the learning rate, which is the value that is added or subtracted, is 0.001, I believe. Now, here, this is different, right? Notice here I made a note, y-test data can be integers and does not need to be one-hot encoded with this function. So someone was asking, right? So you used to actually, like when TensorFlow 1 was, the first one that was available, you had to do all this manually. You couldn't even print the shapes. That's how bad it was. And now you can print shapes. You don't have to worry about these things. But anyway, so as I've said several times, in machine learning, there's essentially just 2 loss functions. For regression problems, when you're predicting real valued numbers, MSE. or a variant of MSE, like there's mean absolute error or something like that, but it's essentially the same idea, right? And there's cross entropy. MSE is super intuitive, and cross entropy is not intuitive. Okay, so I will do a theory-based lecture or two on MSE and cross entropy. But I think, once we do that, it should become very clear. Okay, cross entropy is actually very nice. It comes from entropy itself, like the actual concept of entropy from there. So, but we'll cover that probably next week. So for now, what you should know, use cross entropy. It should it blows my mind, to be honest, that I use this function to train this simple classifier, and I also use this simple function to train the GPT. Like ChatGPT, whatever, they're still using cross entropy. Right? So we only have one gradient descent algorithm, the one we use, stochastic gradient descent, which was perfected by Jeffrey Hinton, right? And then that's the algorithm of training. And then as far as the loss functions, there's essentially just two and variants of each of those, right? But there's just two. Cross entropy for classification when it's discrete things that we're trying to predict, or regression when it's real valued numbers. Got it? All right. So that's pretty amazing, actually. All right. So once I've created loss FN, I have all my parameters, so I can proceed to train. Okay? Yes. Yeah, I'm going to do that right now. Exactly. So I'm going to run this. And remember, I added this code here just so that we can visualize the shapes of our tensors. Okay? So let's go ahead and do that. So I'm going to hit run here. And it's training. And there it is, right? So I paused it, and this is what I was saying. Blast, right? Blast?
Yes.
Yeah. So you can see this is exactly what I had said. 32, just 32, which is equivalent to 32 comma 1. It's the same thing. Or 32 comma 7. You guys see that? So 32 should be the real data, YB. Okay. So we go over here. There it is. The first one is YB, the real data, not one hot encoded. And then YPRED, because it has that architecture that it's predicting 7 neurons, it should be 32 comma 7. And those two tensors are going where? So that this was the question, actually. So if you notice, I printed this one and this one, and that's what goes into loss FN. So I'm essentially comparing this YB, which goes in here, the real data, 32, or think of it as 32 comma 1, versus YPRED, which is the predicted tensor, which is this one, which is definitely 32 comma 7. That's it. This is actually like a mechanical trick. Think of it as like code implementation, or it's not about neural networks. It's about making your life easier. Really, in reality, like mathematically, I should say, what's happening is a tensor that is 32 comma 11, no, sorry, 32 comma 7 is being compared to a tensor that is 32 comma 7. Do you see that internally and mathematically? But in the program, in the code, they go in different shapes, and loss FN handles this. If you're still confused about it, pretty simple. Go to the Torch website and look up nn.cross-entropy-loss, and it'll say, like, okay, when you add the values in here, the first one should be a 32 comma 7, and the second one just 32. Or another way of saying that, one is one hot encoded, the other one isn't. And we will handle it internally. Okay? Any other questions? All right, great. So I'm gonna stop this part here, and I'm going to remove this piece of code because we don't need it anymore. This was just for debugging purposes. I'm going to remove that input. All right. And now we can proceed to train our model. So I've updated the function, and now let's go ahead and train it. Now, what do you expect about the performance of this model? Do you think it's going to be really good or not great? Why? Why not good? The imbalance, exactly. There's 7 classes, but 3 of them are not well represented. Yet they're as important as the ones that are well represented. So the performance overall is going to be pretty bad. Okay. So I've already mentioned if you wanted to improve things, a better solution is to just summarize the 7 classes into just 3, distributed better, or drop some of them. You can do that too. All right, so it is currently training. I think it's going to do 1,000 iterations. If we look at the loss function, it does go down, but it's kind of all over the place. Do you see that? And that's because the class imbalance. You guys are presenting your GPTs today, right? And one thing you probably saw with GPTs, those losses go down nicely, right? Or, maybe not as pronounced, but they do go down. Well, I'll see your presentation, but my observation is I'm always like, I admire how GPTs have this very nice behavior of the losses going down, whereas I'm used to seeing this all the time, which is not great. But it's because your data is usually the culprit. It's not balanced. You can see this is not nice. I don't like this. It started at 188, and at least in the 3rd iteration, this should have made a big drop, and it didn't. It's actually, again, it goes back to 180, so this is not a great data set to work with. It's almost impossible, actually. I mean, you can give it as much architecture as you want and tricks. It's still a very hard problem to solve because, it's highly imbalanced. You really should do something to the data, like removing or reducing the number of classes from 7 to 11. Or sorry, 7 to 3. All right, so it finished. So it's done. So now we're ready to evaluate the performance. How do we evaluate performance of classification? We use that function, right? So this one, print metrics. You can just use this function. Okay, and now we're going to look at the performance. Remember that when looking at the test set, we use with Torch no grad, and that's just because every time we run that computational graph, we could be updating the weights. So we don't want to do that, right, when we're exposing the model to the test set. So this prevents that. We're basically putting it in like inference mode. Notice here, all we do is we're going to do 1 iteration because we only have 1 batch of all 1,000 samples. Remember that? We set this up when we created the test DL. We set the batch size equal to all samples. So we grab X real, Y real. We run X real through the model. Gives us Y pred. Notice here, we have to use this function. Do you see that? Because what does this return? It returns 1,000, 7, right? But our YB is 1,000, 1, right? So what we need to do is we use this function torch max. What is torch max doing? It's returning the index of the highest value. Do you guys understand that idea? Right? So for one sample of the 6 classes, it looks at all, or 7 classes, it looks at all 7 probabilities, and it picks the index of the highest probability. Questions about that? Perfect. All right, so I get my values, indices becomes preds, and then I send preds and reals into the print metrics function. Oh. SDL is not defined. Did I not run that cell? I didn't. There we are. Okay, so that's test DL. And now, okay. So what can you tell me about the results? Is accuracy a reliable predictor here? Actually, it's very consistent with all the other values, but that's because I think they're all terrible, right? But usually when you have a highly imbalanced data set, accuracy is not a reasonable metric. And instead, you should always look at F measure. That's the one. If you can only look at one metric, you'll look at F measure. Precision and recall have other meanings. So this we need to do a lecture on, maybe next week, of what the difference is. Now that you are starting to want to know what these values mean, we'll do a lecture that should clear it up. It's very easy because it all depends on the confusion matrix. So here we can see that the F measure is 0.52. This is really bad. We can see that there was a lot of misclassifications. If you remember, we want the values to be on the diagonal, and then off diagonal should be zeros, essentially. But we don't have that. Look here, for instance, 115 and 170, that's too high, right? So it should be, it should be what, like 300 or more. So these are the problems with when you have class imbalance. Do you guys see that? Any questions on that? It's a hard problem. It's machine learning or deep learning is not going to solve this. What solves this? Fixing the data. Okay? Yeah. So garbage in, garbage out. You guys have heard of that term, right? I mean, you can throw a GPT at this, it won't do anything, right? So what you need to do is fix the data, and then you'll get better results. So 3 classes, for instance. So even though I'm not going to do this in class, as an exercise for you guys, you might want to at home, take it as a challenge to reduce the number of classes from 7 to 3, and then rerun all of this and see if the performance goes up. Got it? All right, great. So yeah, we're almost done, and then we'll start with the presentations. But we've completed these 3 scripts that I think, I'll repeat, I think if there's only one thing you take away from this class is these scripts. The iris classification and regression with wine quality and classification with wine quality. These are the core things to understand so that you can build upon these as you start looking at other things. We've covered GPTs, of course, so you have a contrast between the most complicated, I would say, algorithm in machine learning versus the simplest algorithms. And the linear regression one that we did last week was the easiest. Got it? All right, great. So let's just finish up. So we did this. The performance is really bad. Now we can try another architecture, which in this case is going to be our DLNet. So we're just going to explore this one a little bit more. And again, we're going to look at the architecture here. So you can see now I'm changing, same approach, a class. I'm going to call it DLNet. It's a two hidden layers. I'm inheriting an end module. I have my 2 functions, which are the init function, the constructor, and then I have the forward function, right? I'm going to have now, I pass x means and x deviations, starts at 11, right? Because that's the input vector. First layer is 15, second layer is 9, and the output is still 7. 2 ReLU activations, and the softmax at the end. pretty easy. Okay, then over here, X comes in. We standardize it, goes into linear 1, then activation 1. Again, ignore these dropouts for now, but that's where they would go. Then it goes into the next linear 2, activation 2, and finally the last linear 3 and activation 3, which is the softmax. Okay. All right, so we can draw this one. So it's 11, 15, 9, and 7. Okay, so this one is 11, the input, 15, 9, and 7. Remember, this is the output. So these would be hidden 1, hidden 2. So there's literally 15 neurons and 9 neurons. And this one has 7. Remember, there's an activation function here, which is ReLU. We've talked about it already. It's the hockey stick. And then this one also has an activation function, which is ReLU. And this one has the softmax. That's it. Oh yeah, go ahead, please. You have to go? You can't wait a little bit to do your presentation? It's okay if you can't. You can do it next week. Yeah, it's fine. Yeah, sorry, I thought you could wait longer. That's fine. That's fine. Yeah, next week, that's fine. Don't worry about it. All right. Yeah, so we're gonna wrap up. Any questions on the architecture, how this diagram ties into the code? So definitely on exam 2, there will be a lot of questions where I give you code and I ask for the diagram, or I give you the diagram and I ask for code, whether it's regression or classification. That's like, by now you should see that this is where you make changes, right? All right, great. So it seems like there's no questions. Now let's go back to our code. So this is my DLNet. I'm going to run it now. Okay, so that's instantiated. And the next step then, so this was MLP, is to run these. Okay, so notice now the only difference is I'm changing. This is what's really nice about this approach, right? So it's the exact same code, almost like a template. You just changed this from MLPNet to DLNet. Same optimizer, cross entropy is the same, and so on. All right, so we run it, and it's going to start training, as you can see. Don't expect the DLNet to do better. You know, as I said, we have really bad data. And so you should really think at this stage, what you have to do is really think about your problem. Does it really need to be the way that I have it? You see that, and that's where you talk maybe to your client or whatever, and you start thinking, okay, this doesn't work because it's highly imbalanced. What do you want me to do to improve it? That's just the data is like that, right? Or collect better data. That's another option. Maybe you're just not collecting the data correctly. All right, but yeah. Anyway, so we're running it. You can see the loss function is still not great. From 182, you have another 1.8 here. I don't like to see that. I like these. I like it when the loss, sometimes also what happens is you have nice losses actually that go down, but then when you run the performance is not that great. But I do prefer that. I always show people it did learn. You can see it learned, right? So that's my way out of it. But anyway, this is like the worst. Definitely you don't want that. All right, so let's give it a minute or two to finish training, and then we can evaluate performance, of course. This is the code. I think it's doing 1,000 iterations. I mean, things to consider here, you can try different learning rates, more training time, but I can already say that it's too highly imbalanced. Like this is not ideal. This here. All right, so I'm going to paste in this code while it's finishing. All right, so it finished. Now I'm going to go ahead and run performance is actually worse. 0.43, do you see that? That's even worse than the other one, which was 0.52. Make sense? Yeah. So anyway, this was meant to be, so yeah, so you can see the confusion matrix. This was meant to be a case where it's a really hard problem, right? We can do all these examples like Iris, which is going to give us almost perfect performance, but that's not really where you're going to learn how it works, right? It's when you find these really hard data sets that you're on the other end, right? That it breaks. So, okay, so yeah, that's it as far as this Jupyter notebook. I'm done. So this actually concludes a sequence, as I said, that I was doing, which is these how to model regression, how to do regression and classification problems. Very critical, something very important, right? That in your workplace, there's always going to be some kind of an Excel spreadsheet or a SQL database with data, and people may want to model that. And usually this is how you'll start. You do a classification or a regression. Okay. So I think at this point, you guys are capable of doing that. That would be my stamp. You're ready to go. So yeah, so I'm gonna give you a homework assignment. As I said, you find your own data sets, and you're gonna do a regression and a classification, and you're gonna deploy the models, which is the last thing I need to do. I'll show how to do that next week. For the next couple of weeks, we have to dive into some of these key things, right? Like what is precision recall F measures? That's theoretical. We need to know what cross entropy is. You will never do that in an analysis, right? Because you're just going to you're going to assign cross entropy to loss Fn, and that's it. But you want to understand how it works, right? So that's also theoretical with code though. So we will cover that in the next couple of weeks, cross entropy, precision recall. We just have to go in a little bit deep into how some of this works. Gradients, the derivative, losses, calculus, a lot of that is theoretical things. So this is where I usually cover that over the next 2 or 3 weeks. And then we're going to come back to something called neural input optimizations, very, very exciting technique. So that's actually a different kind of a technique. And I think that'll be the second third of the semester. All right. And then the third of the semester, as I said, is images. So we're going to do CNNs to conclude with stable diffusion. Got it? All right. So yeah, so it's 7:50. We can stop here and then just look for the homework assignment sometime this weekend. I will be posting that. All right, so I will end this video.